Thank you, Stefan. And thanks, Lionel. It's always a privilege and a lot of fun to come to the BayesiaLab conferences, and the hospitality has always been great. And thank you. As Stefan has mentioned, we've worked with BayesiaLab for a long time, and I'll talk a bit about that. But before getting started, just like to mention our affiliation of mine, when I'm saying our in this context, is myself and Yang Zhang, who you saw yesterday present the segment analysis piece. We're in a department called Data and Modeling Sciences within Procter & Gamble in our corporate function. So we span all of our business units. So our business units would be like our fabric care, which is Tide and Gain and those products, or baby care, Pampers and Loves. So our work spans all those business units. And recently we've also included a lot of cross-functional work and a lot of cross-functional interaction, as we were discussing at lunch here, with our IT data science folks as well. But data and modeling science is special because we combine all of that first principles engineering and scientific modeling, like computational fluid dynamics, finite element analysis, chemical process systems modeling, which is the organization which I joined the company, with statistics, data science, machine learning, artificial intelligence. We're all organized in that same place, in that same division, reporting to the same director, and then up through our vice president. My talk is going to be about these aspects, and it's kind of merging a couple of ideas and things. The prevalence of Bayesian applications, I'll only speak about that in context of P&G. This is basically a reduction of a 45-minute talk, which is a reduction of a 7-week course on Bayesian analysis that I'm in the process of preparing for the University of Cincinnati Business College, their Lindner College of Business. They've got a 1-year master's program in business analytics. And so this is you're gonna get the 25-minute version of a 7-week course here. And so the key concepts are really where all the work and meat is. I'll try and illustrate that a bit with a couple of applications, but you're just getting the tip of the iceberg of a lot of material. So I'm gonna try not to break Mick's record of going over time, but it's gonna be tough. So on the Bayesian analysis within Procter & Gamble, it really started about the time I joined the company. I joined in 99, and actually November 1999, so I'm hitting just yesterday was my 19th anniversary with the company as an experienced hire. I worked in the process industries and then joined P&G. My first application was a hierarchical Bayesian model that predicted the color preferences of consumers, both their detection ability, can they detect differences in color shades, and also which did they really prefer, and map that out in a 3D color space. And it led to the Dawn you see on the shelves today, because I don't know how many of you remember, but at that time, dishwashing liquid was mainly sold in opaque bottles, and we just moved to the PET plastic, the PET plastic bottles, which were clear. And Colgate-Palmolive was coming out with this rainbow, and we were stuck on, well, our stuff doesn't look so good if you just take it out of the opaque one and put it in clear. What's the best color? And we came up with this out of that study. But since 2008, we've had this strategic partnership with BayesiaLab, and that's really just been borne out by co-development with Lionel and I guess Dennis, who was always our go-to man to sort out some of the license server bugs. But here are 22 capabilities topped off with the last 3 that you saw yesterday from Yang Zhang. And we've applied this in many different contexts, but I introduced BBN to the company mainly for our products researchers, as we call them. They're like a hybrid between product development and marketing research to process usage surveys, like some of the satisfaction surveys you've seen throughout the day, and derive insights about what's driving people's preference and how the different brands weigh out. What benefits benefit buttons, if you will, should we be pushing to delight a consumer in each area? And so Yang has carried on that tradition with the latest 3 innovations. So I'll talk a little bit, this is more the philosophical part where you get to hear my philosophy on why Bayesian analysis is so important, why we need to leverage it, or probably what you're doing with Bayesian belief networks is just a starting point for leveraging it more broadly. But to learn about it in a certain way as a form of transforming information to solve decision problems, that's entirely useful across all the domains you can apply it. Scientific domains, social science, physical science, social science, business, decision making, et cetera. And we kind of are stuck, or if you come as a statistician or learn through that pathway, the Bayesian analysis, well, Bayesian analysis is you slap a prior on your probabilities, and you just turn a crank and you get out a number that's nominally different from the maximum likelihood estimation. Oh yeah, and you can talk about uncertainty directly and differently than confidence intervals. Done. But that has never convinced anyone to start using Bayesian analysis in our company versus going to software like SAS Institute's Jump and just pressing a button and getting out a regression analysis. And it's because it really sells short the sort of Bayesian mindset and how to think about probability and information processing, et cetera. So I wanted to touch on that. We're talking about how information influences the types of models you build and that structure of the model. You know, that structure of the model really comes from just three sources: that a willingness or a desire to represent your domain knowledge, or some theory hypothesis about a causal mechanism of how things work, some mathematical approximations you have to do just for tractability so you can solve the darn thing, and then some data considerations. Just some mix of that. Like you may go non-parametric because you have a ton of data, you have no real deep knowledge, and you might as well just throw a bunch of basis functions, neural nets, whatever, nodes at it and capture that. And those three sources blend in all the different paradigms. So I like to lay it out this way for all you chemists or chemical-oriented folks. Myself and Young, we're chemical engineers by training. We look at it in terms of a mixture diagram, three components: that knowledge influence, that approximation through the math influence, and that data influence in setting structure. Going vertically, so in these diagrams, the base flat facet, that line at the bottom labeled empirical, is the zero level for what's the vertex opposite that line. So going from empirical to causal, or for the mass approximation, going to purely exact, well, there are very few models, if any, that are non-trivial where you'd have exact representation and using different approximations, or going from a fixed structure, immutable with respect to how the data come in. The data estimate the parameter, but the structure won't change, like in a linear regression, to a non-parametric representation where the structure of the model is eminently flexible. Even the number of nodes, that M in the summation will increase to accommodate the data. And you can see how everything's kind of sorts out and falls out like the physical sciences and social sciences and first principles layout, and then you get into the more traditional stuff, how most people enter into statistical learning through linear regression, and GLM is generalized linear models where you slap a link function and assume some distributional aspects. So like logistic regression, things like in that multivariate analysis, principal component analysis, partial least squares. Then you move over to all the non-parametric stuff and let the data speak for themselves, almost with no way or very limited way of influencing that structure, the learning, to include an inductive bias, as it's termed in machine learning, based on your domain knowledge. And then moving back up towards like case-based reasoning, where you use all these individual cases from which to derive the knowledge, but you're trying to merge it much more with some of your domain knowledge. And I've got things like deep learning neural networks. The actual positions aren't so important in terms of precise proportions like a regular ternary diagram, but it's the relationships. And things are like this because we take very complex decision problems that really would reside in the middle, where you need all your domain knowledge, all your ability to make it tractable and simplify through approximations, and new evidence and observations, all your data. Almost every real world money-making problem lies right in the center of this diagram. And we drive things out to the end because we decompose our problems in a reasonable way to make them tractable, easy to solve, and more importantly, to explain why things work. So even though we may be out in the corners away from the knowledge one, we actually have decomposed things a priori so that when we get an answer, we kind of know the sort of causal way that that information should come back in to help inform us about the decision problem we're answering. And so I look at it this way, driving things simple out to the edges, and then there's the coming back together that's usually done in a very informal, like the team gets together, the PowerPoint is made, the client comes in, our consumer research, marketing research suppliers bring their big PowerPoint deck, and they synthesize all that information into the insights and takeaways in the center of this graph that drives the business action. And what's really been driving a lot, so this lays out all of those things and why I call it simple versus complex, et cetera. But what's driving things now is with computational power, with the desire to do things faster and more automated ways, and especially the advent of direct-to-consumer web-based models of doing business models, there's a desire to drive things back together in a more systematic, consistent way and automate some of the action taking. So make the decision at heart or give advice and just wait for someone to say, go ahead to execute the action. And so that starts bringing more of these hybrid models and different ways of synthesizing the information back to a higher level of a decision. And most of what you do, and you'll see many different ways of doing this. And by the way, lots of money is being made, especially in those lower two corners, just by doing those simple things and inferring them. But it's thought there's more money to be made, or the stakes are higher, and larger policy learning can be made if you can bring things back in through hybrid models and through these more multimodal AI, so taking video, text, speech, all of that together, understanding exactly what your customers are thinking and driving things that way. But the traditional ways are being done, or even the state of the art, like these visual question answering, transparency by design, is all being done algorithmically with procedural methods. And the sweet spot for this Bayesian sense-making, I see it, is you have a unified paradigm that expands throughout this whole diagram and brings it all together under one probabilistic umbrella. Now that may just seem sort of like semantics or like a techie nicety, but what that does is give you consistency, robustness, coherence, all of these nice properties that tell you it works, it hangs together, these are real, and can be automated, and can be computerized and done in a more standard, scalable way. And that scalability with reliability, with robustness, is critical for enterprises like us. And that's driving us to model-based machine learning, where you have a declarative, probabilistic specification of your model, and then all the algorithms for inference, optimization, simulation, et cetera, all refer to that same singularly defined declarative specification, which you got right just once and don't have to rejigger every time you want to do a different optimization problem, a different inference problem. And that's really gives us power, not just in the a productivity play in terms of efficiency, but in insights. It lets people think about the problems differently and answer their problems differently. And so I'll show the landscape in a Bayesian way. Well, I would mention, this is happening in different ways, and you'll see it in the academia and papers, you'll see it in applications, and even in business models of companies, where they're taking more traditional ways and just gluing them back together probabilistically, or they're taking probabilistic pieces, decomposed, simplified, solved, answer things, and then bring them back probabilistically, or they're starting in the whole hairy mess of the difficult decision problem and specifying that probabilistically. That's variant B, and solving it that way. And so the general takeaway here is to impose more knowledge into your models inherently, and the most consistent, reliable way of doing that is in a probabilistic paradigm. And I lay these out just to show that these dark circles, expert-based BBN, data-learned BBN, that's really the sweet spots of BayesiaLab, where we've been able to leverage those in our businesses. And the decision pieces around influence diagrams is something we've also tried and are trying to push, but have been slower because those start to encroach more and more on the human decision-making domain. And so the explanation required, the adoption required is a lot harder culturally and organizationally, but that's more aspirational. And that too is within BayesiaLab. But we're also looking, oh, and I would mention all of this again is framed by a singular paradigm, probabilistic graphical models. So when you see a probabilistic graphical model, all those conditional independencies, you know, what leads to what, what's mediating what, and what's conditionally independent of what, that's all inherently apparent. So getting whole organizations trained in the language of probability and DAGs, directed acyclic graphs, is really important. So you can very rapidly communicate ideas. So we go to whiteboards and just draw this up, and it doesn't matter what domain of science your expertise is in, or whether you're a statistician or data science working on a business problem, and now we're working on a consumer insight or a process fault diagnosis or a biological synthesis problem. We all can understand the same thing. And sort of the golden prize here is to apply things. I see Jackie's there. You've mentioned the master algorithm from Pedro Dominguez, his book. But this is in that spirit of driving in that direction, this fusion of the declarative probabilistic paradigm with the procedural algorithmic paradigm, and bringing them together. In the seminal work, or the banner work, state-of-the-art work, is by Josh Tenenbaum out of MIT's Brain and Cognitive Sciences Science Department, and their MIT AI, or Quest for Intelligence endeavor. But the whole point is that all of this is consistent, and there's a lot to be gained by moving that way. So now I'm going to go into the conceptual pieces that I think make up this paradigm, and talk a bit about how they're applied to actually make money, make decisions out of it. I've got basically two case studies. The one that I didn't have to get any approval from our managers or business unit clients or anything deals with this. So this A daughter is my daughter, as she picked which college to visit and apply to. And it goes through that really intense, highly agonized space where we were fortunate enough at that time, Kaggle made the U.S. Department of Education's college scorecard database available. So this is some, 10,000 colleges and universities in America, all of their information on the demographics, the cost structure, the disciplines, earnings afterwards. So everything about the students coming in, what they're doing there and where are they going out, and all the geospatial information, whether you're urban, rural campus, et cetera. All of that information's there. And that's on Kaggle. So I took a stab at, basically, I wrote it up in December of 2015, submitted in the week of, I think it was the second week of Jan 2016, as a script to Kaggle. And I won a t-shirt for being the script of the week. So if you want to see some old Kaggle history, go to their blog and you'll find an article that describes where they did an email interview with me of what drove that application. But I'll use that a little bit in some of this. But these are the key concepts here that I wanted to stress, that if you could get these down, get them right, and get clarity and conciseness in explaining that, and especially if we can get a nice, concise narrative for our managers to understand and the decision makers, then as data scientists or as the analytics and analysis or math modelers of the space, you get ahead quite far by having them understand these pieces. We're also looking at, and part of my motivation for teaching the 7-week course on this is to emphasize these pieces for new students coming out of universities with degrees in business analytics, data science, et cetera, to understand these principles well. None of this is, I would say, complete in the sense of being 100% thorough or sufficient or necessary in both of those cases, but I think they're important for what we're looking at. So the first is representing things by probabilistic graphical models. I give this as a canonical space here where you have stimuli that usually interventional things, in our cases, for example, product design manipulation, a latent space designing things. In most of our examples, on what I'm working on lately, this is the cognitive structure of a consumer's mind on what's really exciting them, how their needs and attitudes drive what motivates them to act, and where their desires, their wants lie in the space is specified by what product benefits can be delivered, and then how that's manifest in many different contexts. So I just laid it out as these big blobs, but each of these sections, think of them as potential whole networks, whether they be deep learning neural networks, or maybe they'll be images, text, speech, whatever for the observed responses. But the key is we can tie all of them together because we're trying to learn about the same kernel underlying causal structure so we can gain insights and understand why people are doing what and make optimal interventions on the stimuli and context to drive those people to do what we want, what makes us money. And so the whole idea here is emphasizing the highlighted in cyan, the latent space, understanding and modeling the system and not the data, just the observed responses. So it's easy, it's profitable in many contexts just to map data set to data set, and you just forget about everything below the stimuli and the observed responses. But there's value in including that. And finding the applications where that value is most important and how to leverage that is a good piece of what has to be done when you're deciding what approaches to take on model building. One of the beautiful things, though, about this paradigm, if you can lay it out like that, even if you're going to do the modeling at the data to data, all of these nodes have a conditional probability or marginal probability associated with it. So the model that just links data to data, you just marginalize over the latent space. And so mathematically, there's a consistency there. So if you can specify a model with this detail and at least get those parts right, gives you some confidence that you've got the right pieces of information, the right pieces of data to knit together. And we really stress this piece in that latent space is linking all of the information from many different contexts. And so I gave a consumer example, but these can be a business example where you don't understand exactly what your competition is doing or what to do as a marketing action, whatever it might be as that kernel in the latent space, but you have many different signals in terms of sales, consumer surveys, response to ad campaigns, et cetera. An example we have is where you might think people always come to us and talk about our consumers and call them customers, and we're always correcting them. No, our customers are the retailers. Our customers are Walmart, Target, Kroger, et cetera. We have very little direct-to-consumer money revenue. You know, we've got tens and tens of billions going through those customers. In the consumer, we distinguish that language very intentionally, what the consumer needs versus what the customer needs in driving that business. So since we're actually consumers using our product, buying the product, we don't really know like inventory levels within the customer. And so that's a latent variable that's really important for us to get a handle on so our supply chain flows smoothly. So that's an example where it all bears that. So understanding and getting a causal structure in that latent space, we've got tools like B-Key that I'd like to call out as one of the tools we've used in other contexts to understand how the elements come together. And you can, in a very principled way, derive that. The second big piece is information. You know, it was funny, at lunch I was talking with Mick, and he basically described my whole talk in talking about Shannon and information theory, and then going on to, spoiler alert, you know, causality in Yuta Pearl's ladder of causation. Those are the upcoming slides. But, you know, I think once you get in this domain and think about it a certain way, especially coming from a scientific domain or rather than from a statistical data processing domain, it's helpful to think about the information you need to gather and how to represent it in the model structures I went through with the ternary diagram, how to quantify it, how to compare, and how to know when you're doing well, how to know what is imparting information to what through mutual information. All these pieces are laid out in information theory. And one of the reasons why I just jumped on BayesiaLab was it was the first tool off the shelf I could bring, and it had all of these elements written right into it. And as Lionel can tell you, a lot of those apples that fell down, the early ones, were really just ideas I'd had about how information can be used to set different distributions, for example. And we just exchange email. I go home to sleep that night. From France overnight comes an email. There's a new jar file, and we've got the new capability. It was just a beautiful development. See, but you know, I wax nostalgic and get old, and but that's one of the reasons why BayesiaLab is at the forefront, though. The other thing, so we use BayesiaLab principally in BBN space, and now use languages like Stan and PyMC3, you know, transitioning PyMC4. In all of these other incarnations I've tested, and this is an example, again, if you want to go to Kaggle, this is, this link will take you to some work I did on university ranking that helped inform the app I built. Now, I'll go a little deeper on this one. Explanatory and causal inference. So causal inference, causality has been a theme throughout this whole conference. We've seen it in both days and different examples of that. And one thing we haven't used as much in our business is even when we're applying Bayesian methods, getting maximum insights out by driving the right discussion on explaining why things are, or identifying which evidence sets. Evidence set might be the profile for a consumer, or it might be the ingredients needed to make a marketing plan work best. Getting those together, which are the ones that most distinguish success versus failure, you know, delighted consumer versus complaining consumer. And so this paradigm is laid out by Jack Good, illustrates that. I like how he talked about, you know, in discussing this with Alan Turing when he was applying it, you know, in the famous Enigma machine and all of that, and working on code breaking. He just kind of said, I suppose so, when it was brought to his attention that it's Bayes there. And there is just a clear pragmatic, who cares if it's Bayesian or not, just apply it. Now, if you're Alan Turing, you know, that'll get you a long way. You're already a genius. But for most of us, we really have to start thinking about these things more holistically, intentionally, and get it together. I like this quote by Good simply because it's so optimistic, and yet we're so far from achieving it that ordinary people in everyday life, or even in important decision-making contexts, professionals in important decision-making contexts, would apply this structure. I'll give an example here in the way I applied it on our college exploration piece. Here we're ranking colleges as hypotheses, given the student profiles, et cetera. So I can specify as a profile, for example, that listed at the top, these different elements, and I can rank order all the universities in that database with respect to how strongly this, the x-axis is literally just a log scale of the generalized Bayes factor. So this is the weight of evidence for how strongly this evidence supports the hypothesis that the student is at this university. So our hypothesis, the student is at MIT, given this evidence. So you can look at it in terms of prevalence. So the probability of that profile at that college divided by the probability of that profile at any other college. For MIT, that's about a factor of nearly 100 to 1. So it's very much more prevalent in MIT. But it has many different elements here. So which one of these are really driving that? And now you could individually just kind of mix and match, take the pieces out, but that's what computers are for. And so, the most relevant explanation algorithms will actually find that for you. And I'll show over here. So once you've identified the ranking, you can go to MIT and ask, okay, now if the evidence is MIT, what profile is the hypothesis that most strongly supports, explains this evidence? And you find, okay, the discipline being science and engineering, and the SAT scores being greater than 1,400 out of the two-component verbal math, 1,600 total. Oh, well, yeah, that seems obvious. But one of the interesting things is, it's not merely just the more probable case. There's actually going to be more people at MIT who have SAT greater than 1,400 than both SAT greater than 1,400 and science and engineering. Because believe it or not, some of the students at MIT are not science and engineering, yet they had the very high SAT. So the most relevant explanation, or the generalized Bayes factor, will find out even those unique combinations that may in prevalence be relatively low, or at least lower, but they are much more consistent. They set this school apart from other schools than any other combination. And so it's having the degree in science and engineering and getting a SAT high. And so the other thing then is you can contrast colleges, one college versus another. So this is MIT is contrasted with Harvard. And as you might expect, a very high SAT being up here. And you'll see that social science ends up playing in. Interestingly, especially in the light of recent court cases, I guess a side note, is only two ethnicity groups in the categorization pop up, being Asian American or having ethnicity, being American and ethnicity other pop up as being much more probable at Harvard. That sets it apart from other schools. And so that gives you a way of teasing then anytime. So like we'll do a segment analysis, collect the information on how they responded to different elements of a questionnaire, and do exactly one of these most relevant explanation analyses to identify exactly what is that segment of consumers like. How are they so different from everyone else? What was it in their behavior, their responses that was so different? And here's the piece again going to Pearl. I call out Daggity, the tool here, because I found it good mainly for hypothesis formation, but it's also used to set up what needs to be controlled in an experiment if you have that ability, or if you have observational data, what terms should appear as covariates in your regression models versus not. So gather all the data and pour that bucket into your machine learning algorithm, it fails in giving reasonable results for the impact of each of those covariates because they break the rules around including confounders versus not, et cetera. And so Daggity is a tool that's useful for getting that. But, oops, I hit the wrong thing. But more than anything, it's led us to plausible reasoning about some underlying motives for the consumers and how to get to those points. And so I'll go through these fast, but this is how we then went into a latent, I personally for this college exploration tool, went into the latent mindset of a student and some of the aspects I thought would be important and how I parameterized it by for sort of preference or needs that they would be seeking. And that played out then in us being able to do sensitivity analysis, in this case around a student's desiring for a breadth, a broad, very narrow technical or discipline-specific school versus a very broad school, and seeing how the rankings change. So if you're engineering as your discipline you're seeking, and you're looking very, very narrow, low-breadth schools, you see more technically oriented universities, and if you relax that, you pretty much don't care so much about finding all like-degreed people or high emphasis on your discipline at that college, and you get a different ranking over here for the breadth being high. But doing sensitivity analysis and applying all the theoretic decision analysis tools is another piece that's important. And then the final piece on the concepts is how we've used this and how, well, I'll give this example of similar to how we've used this technology in the optimal learning scenario. If you're familiar with a conjoint analysis, you basically have many alternatives, that space that's huge in its dimension. Here I use a toy example of, let's say, coffee cups. You got the color, the shape of the handle, whether it's tall and skinny or short and squat. So that would be like 3 different dimensions. I'll call them A, B, C here. But you can imagine for whether it's ad messages, claims you want to make about your product, and different benefit statements, whatever, you can have hundreds of these in each dimension, and then it's just multiplicatively that grows exponentially. So you have an extremely high dimension, and especially when they're categorical or discrete, you don't have any natural parameterization of that space. So that becomes really hard to do to find out what's really wanted, and you can spend a lot of money. So what people do is just do sufficiency. So the lean framework, just find something that works and move on. Well, you can do better here. So what I show is the probability of someone choosing each of these options. So I line up the cups here to indicate that each of these notations at the bottom and then each of these vertical little elongated footballs represent a probability distribution on where we would expect what percentage of consumers would choose that one over some outside good. And then we have a so-called acquisition function in the Bayesian optimization terminology that we use as a proxy to capture not only what is good, but also what we're most uncertain about. So we want to go fast and high to what's best. We want to exploit what we know, but we don't know much, so we need to explore and learn. So you have this exploration and exploitation that has to be done simultaneously. You don't want to waste money learning everything perfectly by serving up crap. And that's what you would do in a regular design of experiments. Some of the alternatives will be horrible, but you just weather that because you're learning. Here we need to learn in real time, and we don't want to lose a customer as we're learning. And so you perform that experiment. In this case, I have put 4 cups in front of the consumer. They choose one as their best. You use that information and update your model. So which 4 cups do you put in front of them? And that's what the acquisition function is for. You take the top 4 in this line. So at start is basically random. Put those in front of the consumer and let them pick. So the first round, okay, sometimes you're going to serve up trash. And from what you learned there, Through variable selection, Bayesian variable selection, you learn which attributes resonate with the consumer, and you can identify with some uncertainty where they are. You update the model, and so you then evaluate, well, now the 4 things that were put there, you know them really well where they are. You learn also, because these have shared attributes, you learn also about some of the other alternatives, especially things that share 2 of the 3 of the thing that you put out there. And so the acquisition function updates, so the stuff you really know about, yeah, it could be better, but not much better. And the stuff you don't know about, yeah, you get a different ranking. So you pick the top 4 from the acquisition function, put them in front of the consumer, she picks 1, you update your model. Now you've learned about more features in this very high dimensional space, and then you update. So I've jumped from wave 1 up to wave 5 of doing this. Now what I've talked about here is just like these batches, and you do that. But imagine doing this 24/7, asynchronously, automatically generating all the options. And also, some of these are like sending a sachet of a perfume to a consumer or a shampoo and getting back feedback, and you just run your business this way. Some of the information's coming from a web page where someone's clicking through your product catalog and then putting it in their shopping cart, and that's their choice, and you run that information back. So knowing this generalized paradigm of probabilistic graphical models, you go from just the simple conjoint model, the discrete choice model we used in the update piece here, to a full-blown consumer preference model with all of these different ways of measuring an indication of that preference and letting them all vote on all the propositions that you could design and throw out to them or that are in your product catalog. And you just run this 24/7 and you got a business. Now for us, is that business a $1 billion a year one? I don't know. For an entrepreneur, they'll settle for 10 million a year and be quite happy. And so that's how this functions. Now we've written a paper, came out just last month in management science. Professor Max Zhu, he was at Ohio State University in Columbus. That's where I worked with him. Now he's at University of California, Riverside. And we work with Greg Allenby as well, who's the I guess, godfather of Bayesian statistics and marketing. And so the result was this. If you're interested, you can go online. And it's still the same face, so you don't know if she's happy or not, but she applied and she's at Harvard now. So it worked out all the best. She got into her dream school. So I just like to close by touching barely, just mentioning, okay, these are the big places things are going. One-shot learning by using the Bayesian program learning. Explanatory AI, that merger of this probabilistic in procedural, declarative and procedural. Learning at the edges where now you don't even have to gather all the personalized information of your consumer. You just, every consumer is a parameter vector in your larger model. They're running their individual level customized models on their smartphone that tends to their needs. And with every action, you're updating that, bringing it back to the mothership model to use Bayesian multi-level model to update what's known about everybody in a heterogeneous way. And so any new customer, you can be very responsive to what they want. I think the best in practices then, we're organized, I described our data and modeling and sciences organization. We're organized to leverage this technology, and I see academic initiatives like the MIT Quest for Intelligence going that way. And also, these are some notable business models that are out there. In fact, Qualcomm is also doing the computing at the edge through federated learning pieces. And one way of keeping up to date, I curate a Flipboard magazine that just called Bayesian, that almost on a daily basis, I just collect, make a mashup of what's out there in these spaces. And so that's the final slide here. I just wanted to note amongst the references, these two characters, Stefan Conradi and Lionel Juf, is some of the best in class in explaining how to apply this for drivers analysis and their probabilistic SEM approaches. So thank you.